Hi, this is Joe Maciars from A Tutoring Enterprises with another Apple Graph or Math video. We're continuing with the graphing rational functions, and specifically we're looking at holes in rational functions. This is the last in the series of 4 videos on this topic. We are going to have some example videos after this, but that will take care of the theory. Here's a little plug for my business. At A Tutoring Enterprises, I'm in online and in-person tutoring in physics, math, and engineering. Alright, let's get back to the Apple Grapher video, or the Apple Grapher application. The star of today's graphing equation, if you will, is y equals x minus 2 squared over x minus 2 squared. Now, of course, the x minus 2 squareds are going to cancel, and we're going to get 1, so y equals 1, and that's exactly what you're seeing being graphed. However, there's going to be a little bit of a surprise with this, and we're going to see that in a little bit later. What I'm going to do first is summarize some of the things that we've learned in the last 3 videos, because we sort of need that here. So this way you can look at it here without having to necessarily go back. One of the things we looked at was vertical asymptotes. We looked at an equation like y equals 1 over x minus 2. Let me go ahead and put that in. And we saw that there was basically something called a vertical asymptote and a horizontal asymptote. We actually saw more of that in the last video. But these two things together are the asymptotes associated with y equals 1 over x minus 2. Now, the x minus 2 to the first power was called the power was called the multiplicity, and the multiplicity had a specific behavior to it. For example, when it was 1, we saw this type of graph with the green lines, green curves. When I made the exponent 2, both branches of the curve would go up in the same direction. Okay? When it was 3, opposite directions, and when it was 4, same direction. So basically, any even multiplicity, even exponent, made the graph go in the same direction as it approached the vertical asymptote, whereas an odd multiplicity basically made them go in opposite directions. That was the first thing we learned in the 3 videos ago, basically. All right, let's turn these all off. The second to last video was equations where we were looking at the multiplicity on the top. That is, we can think of this as x minus 2 over 1, and the multiplicity right now is a 1. Well, this is just a linear equation, y equals x minus 2. The y-intercept is negative 2, and the slope is 1. What's really important here, though, is to notice that there's an x-intercept at x equals 2, and there it is. Okay. Now, the behavior that we saw associated with this was that if the multiplicity was even, then the graph would just come down and just touch the x-axis. If it was odd, it would pass through. Even, just touch, odd, pass through. So that was the behavior associated with the top. We're going to be combining both of these behaviors. One of the other things we saw in the last video, just to summarize very quickly, was looking at the extreme end behavior of equations like this. Now, actually, I want to start out with this 4 that's up here to be a 1. And if I hit return, we're going to get a fairly complicated graph that looks a little bit like this. Now, we're not really worried about the details. What we're worried about is what happens when x becomes very big. When that happens, we can basically ignore the negative 7 that's on the top and the negative 5x minus 7 on the bottom. That is, we're only concerned with the highest order terms. Highest order means the term that has a variable to some high power, the highest power in that particular factor, if you will. So 2x squared is the highest term, whereas on the top, 3x to the first is the highest term. Well, ignoring the rest of this stuff, what do we have then? Well, we have 3x to the first over 2x squared, and one of the x's is going to cancel. And that's going to leave us with something that looks like y equals 3 over 2x. Okay? And that's going to be, well, kind of our middle behavior in reality, because when we let x go to infinity, even in this one, what's going to happen is we're going to get y equals 0 as our asymptote. So we really sort of have 2 asymptotes, one which is what I would call the extreme end behavior, and this is more what we might call the middle behavior. Now, even the middle behavior is not quite right here because basically there might be some adjustments that would actually make this become closer to the actual asymptote that we're getting from this. But we're not concerned with that. We're concerned with when x becomes really big. Okay, in order to see that, let me zoom out. And as I zoom out, you're going to see that at this end, basically all three curves, and over at this end, all three curves are basically becoming the same thing. We're not going to be real concerned with what's happening in the middle. This is our extreme end behavior. If we zoom out even more, it becomes more obvious. Okay? All right, let me zoom back in. All right. Now, we also examined what happened as we changed the power, let's say on the top. That is basically with respect to the bottom. So we could change the bottom or we could change the top. I'm just choosing to change the top. Again, we would be ignoring the negative 7 on the top and the negative 5x minus 7. The highest terms are the 3x squared and the 2x squared top and bottom respectively. The x squareds will cancel and we will get y equals 3 halves. So let me turn this one off and turn this one on. This is now our new asymptote, and what we're going to see is that this graph will start to approach it. We can see it approaching here. We can't even see the other branch over here, but as I zoom out, you're going to start to see it. There it is coming in and beginning to approach the dashed line. And as I zoom out further and further and further, okay, you're going to see the green line and the red dashed lines merging. Okay. Now, in reality, what we probably ought to be doing is just changing the frame limits for this, but I'm not going to do that because I'm just going over this in summary. If you want to see that in more detail, go ahead and look at the actual video. All right. Now let's go ahead and turn this off, go back to this equation, and up this one more time. Let's make it x cubed. So now we have 3x cubed over 2x squared, again ignoring all the rest of this stuff. Two of the x's are going to cancel, and we're going to be left with an x on the top. Well, that's going to give us 3x plus 2, which is going to be a line like that. And so when I hit return here, I guess I already did, we're going to get a graph that looks like this. Now, we're again missing that upper lobe that we're going to see. Let me go ahead and zoom out again, and we'll start to see it in a moment. Okay. And there it is coming in. This part of the graph is going to approach this, and this is going to approach this. Now, it is a little off. There is actually, as I said, an adjustment factor, 3x over 2, and it should be plus something. Actually, in this case, yeah, plus something. You would raise it a little bit. And you would get that by doing some some long division of the polynomials. And we're not going to worry about that here. We'll look at that maybe in one of our examples. But basically, again, as we zoom out, the green line and the red dashed line will basically merge to become 1 as we zoom out. That's the idea, that the extreme end behavior is basically this 3x over 2. All right? And just for the idea, and by the way, this is sort of an odd multiplicity effect here. That is, it's the x to the third over x to the squared gives us basically an x to the first, which is that line. If we make this a fourth power, we're going to have 3x to the fourth over 2x squared. The x squared's canceling, and we're going to end up with 3x squared over 2, which is not this one, but rather this one. Okay, and if I hit return, let's see, I guess I gotta click over here. All right, we can see again the red and the green dashed lines are basically on top of each other. Let me zoom back in and you'll see some of the detail of this. Okay, we're going to very shortly miss that lobe as we zoom in further. That's the lobe that's basically making up the right-hand side of our graph, and the left-hand side is coming from this part of a vertical, well, coming from a vertical asymptote up and matching that parabola, or coming close to it. Let's go ahead and zoom in even more, and you'll start to see that right-hand lobe disappear on us as we go lower and lower, and back to something that looks like this. Okay? So if I were to tell you the green line is a parabola, or mostly a parabola, you might not believe it from this point of view, but as you zoom out, that's exactly what it is. So that's the type of behavior we had been looking at in the last 3 videos. Let me turn these off and close this. But now we're going to go ahead and study this equation. However, it turns out that this equation, let me zoom in one more, actually maybe 2 more. While fairly good on this, as this graphing calculator is, it's actually leaving out something kind of nice, a nice little feature, and you wouldn't know that you were missing this feature unless you saw the other graphing calculator. So we're going to go look at a different graphing calculator now. Let me tell you a little bit about this graphing calculator. This is a called graphing calculator from Pacific Tech. And it's a calculator that's available both for Macs and PCs. So if you've been looking at all these Apple graphing videos and saying, geez, I wish there was something for PCs, well, this is it. It costs about $100, which is about the same price, actually a little bit less than I think a TI-83, unless you can get an 83 or 84 really cheap. I think there's, I don't know if they're not making, I don't think they're making 83s anymore. I don't remember. In any case, it's about the same price as that type of calculator, a little bit less, maybe a little bit more depending upon where you get it. And it's good on both Macs and PCs, so this is the calculator you want. If you're going to be an engineer, a mathematician, or a physicist, or even if you're just going to spend some serious time working on your mathematics, this might be a really good calculator to invest in. Now, let me show you some of the great features about this, actually one great feature about this. And I guess I want to compare that to what we're doing over here. Over here, we're going to look at something that is a trace feature on the other graphing calculators. If I click using this pointer over here on the Apple grapher and I click, I get 2 dashed little black lines that basically tell me the value that I'm at. And this is x equals 3.6223, and that's been rounded, and y equals 1.000, and that's basically been rounded. However, in this case, it's actually the exact same value. Now, as I move this back and forth, you're going to see that I can change my x value, or generically, whoops, changing x or y would work. Okay, but the point that I'm going to make here is that this is sort of an approximate value. For example, if I try to get x to be -1, you're going to see that there's no, I mean, I can come really close. That's probably right in about that neighborhood, is about as close as I'm going to get. Why is it not giving me x equals -1? Well, the reason is because what it's graphing is pixels. You can think of a pixel as a tiny little square, and the coordinates that are given to whether to paint that square or not is associated with the center of that square. And the center of that square, at least in terms of x values, we take to be the very middle of it. So, for example, this is the middle of some pixel. That middle of that pixel is located at -1.0039. The next little pixel is just a little bit over, but it skips 1, or -1. I guess I'm going the wrong way. Go the other way. You can see it's really touchy here to get to it. But, yeah, there. It's just jumping a massive amount if you're considering 3 digits. But this is how these graphing calculators all work. They're only graphing a pixel, and so a lot of times they don't give you the exact value. Now, let me go over to x equals 2, and I just want to go over this point. I want you to listen. As I go over it, just listen for a second. You don't hear anything special. There's nothing going on. If I try to get it to be exactly 2, it's a little bit off. It's not exactly 2, and it's still telling me that y is equal to 1. All right. Now let's go back over to the Pacific Tech calculator, all right, and do the same thing. Now the only problem here is when you click, it automatically goes into this cursor or tracer cursor, and it's a little harder to get out of, as it turns out. So even though it's easier to get in, it's a little harder to get out. But let me go over, and you can see it's doing the same sort of thing. It's actually giving me the middle of a pixel value. For example, right now I'm at 1.25625, and there's been stuff that's been cut off. Okay, and I know that from studying calculus. I'm not going to explain how, but this is not an exact value. It's been a rounded value, and y, however, is an exact value in this case. But listen to what happens when I go over x equals 2. Hear that? There's a little ticking there. And it's kind of like the feel is as if I'm just falling into a little tiny groove, as if I had a marble. I was moving a marble back and forth, and it just fell into a little groove. It's giving us that ticking sound. But look at what it says. It says x equals 2 and y is not a number. That is one of the great features of this particular graphing calculator. Even though it normally would be some middle pixel that would not pick up x equals 2, this software actually says, wait a minute, there's something important around that neighborhood, and I know it would be in this pixel. So what I'm going to do is I'm going to tell the user that this is the special thing that's happening at that point. In this case, it's telling us that there's a hole in this line. And I know it's a little hard to believe because you don't see the hole in any sense. Remember, the hole is just one point out of an infinite set of points. And so even though if we move across here, you can, and this is part of that issue now where I can't get rid of the trace. I haven't found a good way to get out of this trace, and so the trace is right on top of this line. But even if this line was gone, you wouldn't see any hole there. In that case, you actually need something that tells you, yes, there's a hole there, and this is what's doing that. Now, you might object to this. You might say, well, wait a second, don't these cancel, and don't you get 1? Shouldn't this be 1 everywhere? Well, yes, except at x equals 2, because when you put in x equals 2, you put in a 2 for x, you get 2 minus 2, which is 0, both top and bottom. Now, if you take a calculator, a hand calculator, and type in 0 divided by 0, you're going to get an error. And the error is because you're dividing by 0. You can't divide by 0. And so that's what this is. This graphing calculator is really great because it gives you that feature. Let me show you another little quick feature that this graphing calculator does. Let me type in an equation, y equals 3 minus, and I'm going to want parentheses for a little later. I'm going to come back here. 3 minus x squared, and we're going to get a parabola. Let me zoom out a little bit. There we go. All right, so there's our parabola. Notice I've gotten rid of my trace coordinates. Whenever I put in a new equation, it gets rid of those tracer lines. But what I can see now is that I've got a parabola that's upside down, located with a vertex of 3. Okay. Now let me go ahead and click on if it'll click, please click. There we go. And now we'll get our little tracer. And listen again when I approach the vertex. Hear that? It's actually telling me that this is a maximum value. It's a special value, and it's telling me that it's at 0, 3. So those are the coordinates of that. It'll also, if I remember correctly, it also tells me intersection points. So I'm getting a click there, which is kind of nice. And I'm actually getting a click for x-intercepts. So this gives me lots of pertinent information, and that's why this graphing calculator is an advantage to have. Even if you're on a Mac, I would get this as a second calculator because it's so handy for this feature alone. Okay. Let's go back over to the Apple Grapher because that's where we're at now. Now notice on this one, all I've got to do is sort of click off and I can get rid of those lines. It's much easier to get rid of those trace lines. But we notice here again that there's no particular issue at x equals 2. That they're showing. But in reality, there should be. All right. Now, we're going to handle this in just a moment, but let's go ahead now and take advantage of making the top, just like we did earlier, and it's not quite what I want. There we go. A 1. All right, so now our graph looks like this, and this has the same basic form as y equals 1 over x minus 2, and that's because one of the x minus 2's canceled. If I turn this graph on, you'll see that it's a blue line that I've set up ahead of time that's right up on top of the green line. And yeah, that's basically what we want. The horizontal asymptote at that point would be y equals 0. Okay. Let's see, what did I want to talk about here? I want to talk about what happens when, okay, I just want to say that the 2 minus the 1 gives us the 1 that's in the bottom. This is odd multiplicity, and remember the behavior that we saw when we had a higher number in the bottom. Basically what that amounts to is that we're going to get a vertical asymptote, and its multiplicity, the effective multiplicity, is the difference in those two exponents. So for example, if I come down here and make that 2 a 3, it's going to be 3 minus 1, which is going to be 2. We're going to have that in the bottom, so it's x minus 2 squared. It's going to be a vertical asymptote, and in both branches are going to go in the same direction. There you can see that's what's happening. Let me turn this other one off now. Okay, so that's what's going on there. All right, now I'm going to turn this back to 2. So that's our general rule, one lesson for today's video, that we've learned that if the exponent in the bottom is bigger than the exponent in the top for a particular factor, you're going to get a vertical asymptote. Now we also saw just earlier what happens if they're the same. And, sorry, it's a little touchy as to what key you got to hit here. In this case, we saw y equals, or x equals 2 was a hole. We got y equals 1 as our curve. And in this particular case, there's actually a hole at that location. So this is what we're going to use in these circumstances. So when the two powers are the same, it basically acts as if the two factors aren't there, except it puts a hole at the position of this x minus 2. In other words, at x equals 2. All right. Now, let's go ahead and take a look what happens. Let me turn that off. If we go ahead and make the 2 on top a 3. So now we have x minus 2 squared on the bottom, x minus 2 cubed on the top. Two of them are going to cancel, and we're going to be left with something like y equals x minus 2. And so we're going to get a blue line that looks like that. If I turn that blue line off, there's the green line. That's what this is. But there is a subtle difference. This one, the blue one, does not have a hole in it. The green one does, and that hole will now be located there, and it will act like an x-intercept. In reality, the green line, believe it or not, never actually crosses the x-axis because there's a hole there. Because of that, it actually just jumps over the line and keeps right on going. So it's acting like an x-intercept, but it's not. Now after that, we basically get the same sort of behavior. Notice that if this is 3 minus 2, that basically gives us an x minus 2 to the first on the top, and this is acting like the 1 multiplicity on the top, which basically acts like it's passing through the x-axis. I remember that earlier in our discussion. If I make this a 4 now, we're going to have 4 minus 2, which is going to give us x minus 2 squared up on top, and it's going to give us a parabola. Again, a parabola without a vertex, without an x-intercept in this case, but still a parabola, and it's going to act, this hole is going to act like an x-intercept. All right? Okay, well that's almost the end of this video. I just wanted to show you one other quick little thing. I want to go back to the other graphing calculator now, and I wanted to tell you that right now, we now know how to put a hole in any curve. You'll notice here that in this area right here, there's no problems. You're not hearing any clicking. Okay? But if I want to put a hole in the graph, all I've got to do is put in something like x minus 1 over x minus 1. The same thing. As long as I have the same thing, top and bottom, this is now telling me I'm going to have a hole at x equals 1. If I hit return, now, in certain curves, you can actually kind of see the hole. If you look here, I don't know if you can see it on yours. I can see it here now on the screen. There's a little gap in the purple line, and there's actually a little bit of a blue because there's some blue behind our blue grid, and that 1 is on the blue grid, so you're actually seeing it there. Now, the deal is that if I actually zoom in on this, oops, wrong way, zoom in on this, and let me grab my hand, move it down. The hole doesn't really get any bigger, and it shouldn't, again, because it's a single point. The fact that they're even putting a hole there is just a feature that they're trying to put in. It didn't turn out well for them on the first equation where we had basically y equals 1, but it's making a pretty nice hole that we can kind of see in this graph, but it's very easy to miss as well. Let me verify that by putting our tracer on it. And there it is. X equals 1, y is not a number. There's a hole in the parabola right there. Now if I want to change the location of that hole, I can, for example, change the 1 in this to 1.2. and that'll change the location. And okay, I'm not quite seeing it, so it's not, I'm thinking maybe that's it right there. It's a little difficult to see, and it is. Okay, there it is. So x equals 1.2, not a number. So you can do this or put as many holes in as you want. For example, I can put one in there. Let's put one in at x minus well, 0.5 over x minus 0.5. Okay, and now we'll get two holes. One at 0.5, which again I'm not seeing very well here, but there it is. There's the 0.5, and then we should still have one at, there it is, 1.2. Okay, so I don't know why you'd ever want to put holes in your graphs, but now you know how to do it. So there you go. All right, that's the end of our video. We were studying how to graph rational functions. This was the fourth theory video. We're going to now, in the next video, switch over to some examples and take a look at how to apply all of this mess. What we're really interested in is how do I sketch a graph from just looking at the equation, and we're going to look at that next time. Again, this has been A Tutoring Enterprises. My name is Joe Maciars. I do online tutoring and in-person tutoring in physics, math, chemistry, and engineering. That's my information, website, email, and phone number. Give me a call. We'll set you up with an appointment and get you some help. Please remember to hit the like button for the video, comment, and tell me what you think, and subscribe to get updates on all the other videos that I do. And if you think this video helped you, please donate $1 to my PayPal account at 2tent@neb.rr.com. And I'd appreciate that quite a bit. And right here we're going to have a white screen. And the white screen should be filling up with those 3 previous videos that I've been mentioning. Should also show up with the 4 or 5 or whatever videos I'm going to have in the future. I'm also planning on having some sort of a video directory or catalog. I haven't quite decided what to do in that, but look for it in the future. Hopefully I'll get that done sometime this summer, 2013, summer of 2013. Other than that, thanks for watching this video, and I hope you get a chance to look at some of the examples. That should make some of this stuff really clear. Thanks for watching the video, and have a great day.